Hi everyone, so I'm Akshat and I'm here with Sriram today to explain our work on higher order structures for graph explanations. So this work is primarily for graph explainability, which we will introduce in the coming slides. And just as a brief, we use higher order structures called simple cell complexes to aid graph explainers in explaining the predictions of graph neural network better. So let's talk about graphs. So graphs are the most abundant data form you will have, as they are very naturally occurring. So as you can see, we have molecules here that can be represented as graphs for various drug prediction or property prediction tasks. We can have transaction networks as graphs. So a lot of fraud detection work, anomaly detection work is done in transaction networks. We also have social networks, images, and very recently Google has also been using graph neural networks in their Alpha chip, AlphaFold, all of their chip manufacturing stuff and drug prediction stuff. So graphs are very popular, very abundant, and very useful. We now talk about explainability. So again, because it's graphs are being used in very high risk applications such as drug discovery and the fraud detection, etc., etc., it is important that our graph neural networks do not learn spurious correlations. And the only way to know whether graph neural networks are learning spurious correlations or not is for them to be interpretable and for their predictions to be explainable, so that we know exactly why a prediction is being made. So let's take this molecule on the right here. Let's say that the task is that we have to classify a compound as toxic or not. And just as a very elementary example, let's say that if the molecule has a benzene ring, it's toxic. So it is important for the model to learn the correlation between the benzene ring and the toxicity. If not, if it learns some other spurious correlation, it won't be able to classify, it won't be able to generalize to the actual task. So here, as we can say, the correct or the ground truth explanation is the green benzene ring. So we'll keep using this example in the coming slides as well. But I hope you get the point. The point is that the GNNs need to learn the correct causal relationships. So this work was started when we when we realized that graphs themselves have a limitation as a data structure. So if you ever noticed, graphs are made up of nodes and edges. So two nodes are connected by a single edge. So in graphs, we can only model pairwise relationships because one edge only connects two nodes. We cannot have an edge connecting three nodes, right? That doesn't exist in a graph. So what this leads to is when you have, say, like a structure like this, right? So in this structure, the graph, like any graph neural network, will only be able to model these interactions individually. Like it won't be modeling this whole big interaction as a whole, which sometimes, so for example, in the benzene ring, so if you have studied some elementary chemistry, you'll know that the benzene ring is a group interaction of the 6 carbon atoms present in the molecule. But the GNN will treat them as a simple cycle. And it is well known that GNNs do not perform very well on cycle detection. So graphs give GNNs a limitation of not being able to model higher order or multi-node relationships. So what happens is that, as I said, it is hard for graph explainers to capture such interactions. If GNNs themselves are unable to model these higher order interactions, it will be much harder for explainers who are working on the outputs of the GNN to be able to capture the interactions as the explanation. So if we see here, so GNN explainer is one of the first explainers that came out for graph representation learning. And on the task introduced before, we see that GNN explainer actually only gets 2 of the nodes correct from the benzene ring, and the rest are a spurious correlation. So these kind of problems are inherent in explainability, and our work Forge tries to mitigate some of them. So, as we said, the limitations of graphs are pairwise interactions. So, to overcome this limitation, we use a higher order generalization of graphs, and which are called cell complexes. So, cell complexes are like a very easy way to think about them is like, for example, let's say you have the benzene here, and what we will do is we'll think of it like a shape. So like it's basically think of it like a hexagon. So we have nodes here, and we know in a GNN nodes have features. So what we will do is we'll make edges nodes as well. So let's say we'll represent it by a square. So we give each edge its own node, and then if we connect these nodes with the vertices that the actual edge was connected to. So in this way, we've given edges their own features, and we've also maintained the connection that one edge connects two nodes. And then we can go up one more dimension and give this whole face a node, and then connect it to all the edges that comprise the face. So in this way, we've given the whole interaction of 6 nodes a feature vector by itself that can encode the interactions of all these 6 nodes together. So this is the power that cell complexes give us. So to understand various algorithms in our paper, it is important for us to go through some elementary definitions that make up cell complexes. So I'll keep using the running example of the hexagon as a cell complex that I've shown here as an example. So we first talk about a P cell. So P cell is a fundamental component of a cell complex, and it just refers to a cell of dimension P. So in the hexagon that we had nodes for vertices, edges, as well as faces. So here the vertices will be 0-dimensional, which means they will be referred to as 0 cells. Edges are 1-dimensional, so they will be referred to as 1 cells, and faces are 2-dimensional, so they will be referred to as 2 cells. And that's it. That's the only thing we need to know about a P cell. So usually cell complexes extend into higher dimensions. They can have 3-4 dimensions as well. However, we will constrain ourselves to 2 dimensions since most of our practical work is done within 2 dimensions. Next, we have a boundary or a co-boundary. So let's say we take a small piece of that hexagon. So I'm just taking one edge of that hexagon. So here is the edge node or the 1 cell. So now we'll change the terminology and refer to vertices and edges as 0 cells and 1 cells. So here we have 2 0 cells which are connected to one cell. So in a cell complex, a P cell is considered a face or a boundary of a P plus 1 cell if the set of points composing the P cell is a subset of those composing C P plus 1. So all it's saying is that if so this 1 cell is actually constructed from the connection of these 0 cells. So these 2 0 cells actually are called the faces of this 1 cell, and conversely, faces or a boundary, and conversely, this 1 cell is called the co-boundary of these 2 0 cells. So a very easy way to think of it is that like I have 0 cells, 1 cells, 2 cells. If my 1 cell is connected to any 0 cells, those are my boundaries, and if any 0 cells are connected to any 1 cells, those are the co-boundaries of those 0 cells. Or any generalization, you can do this with 1 cells and 2 cells as well. Next, we have a P chain. A P chain is simply just the set of all P-dimensional cells. So this in our hexagon, if we just take 0 cells and create a set out of them, we will have a 0 chain. Similarly with edges and the faces. Next, we have the P skeleton. So a P skeleton is basically so if you have, say, the hexagon again, we have 0 cells, 1 cells, and the 2 cell or the face. So the P skeleton of a cell complex is the subcomplex which consists of cell of dimension at most P. So since here the max dimension is 2 dimensions, so we can construct a 1 skeleton and a 0 skeleton out of this cell complex. And a 1 skeleton will look like us having only 0 and 1 cells, so we just remove the 2 cell. And a 0 cell skeleton will look like removing all the 1 cells as well. So the 0 skeleton is the same as the 0 chain that we saw earlier. However, the 0 skeleton will have connections or edges or boundary relations, as we're about to define. So that's one important distinction between skeleton and chain. Chain is just a set. Skeleton is an actual graph or an actual complex in itself. So we come to the final definition that we need to understand cell complexes, and this is one of the most important definitions because we use it extensively in the coming slides. So a boundary relation, in very simple terms, I know there's a lot written here, but in very simple terms, it's just the analog of an edge in a graph. So here, since we represent edges as one cells and as their own entities, they are no longer just connections as they were in graphs. So here, as I said, each 0 cell is connected to a 1 cell and other 0 cells, etc., etc. So all of these connections that are there in a cell complex, we refer to those as boundary relations. And that's it. That they're just the analog of edges. If you want some more information on how we construct them and what bounds we put on them, you can look at the definition, but it's not necessary. So, as we saw, cell complexes are very powerful in modeling, relationships between nodes. But however, obviously this comes with additional computational costs, as a cell complex is much more dense than a normal graph. So we see that the size actually scales quadratically if we increase the number of edges in a graph, the size of a cell complex will scale quadratically. So formally, we show this in theorem 3.1, where we take a graph having V vertices and E edges, as well as some cycles. We show that the cell complex will have the C cells and sigma boundaries such that the size is bounded as shown in the equation. So the most important thing that we can get out of this equation is this lower bound, which shows that the number of boundary relation actually scales quadratically because of this combination term, because this is basically going to be degree C2, so which scales quadratically as you increase the degree. So yeah, that's the problem with complexes, is that they are very space inefficient. And so there is it's important for us to make them space efficient while still retaining the quality of them modeling the relationships. So what we realize is that if we strategically generate or strategically add the boundary edges, we can bring this space complexity down to linear, which means that the cell complex will actually scale in a straight line with the number of edges as we increase edges. So the relations here I'm talking about in the size, by size I mean the number of boundary relations. So again, as I said, we go back to equation 2, this one. As I said, the last term is what is actually the problem, because the last term is a combination term which scales quadratically, as we saw. So this term actually represents the edges, this term represents the boundary relations that are of this form. So what sigma C11, C21 means is that it's a boundary relation between one cells. So any one cell that we have, so if we go back to our example here, and we have edges as one cells. So any relation that connects these edges is of this form. So what we realize is that we don't really need it to achieve good performance. And removing this term actually helps a lot in the scalability for space. And so what we do is we restrict how we create the cell complexes, and we drop all boundary edges that are of this form. So C11 means edges between a boundary relation between one cell, and also we forbid boundary relations between two cells. So by doing that, the equation reduces to this because the last term is removed, and this ensures that sigma actually increases linearly with the number of edges, which makes cell complexes much more scalable. You can see here our reduced complex is this line, which is scaling linearly, approximately 3 times the number in practice. But when we have the full complex, it's scaling very like at a very fast rate compared to the reduced complex. So as soon as we go to very large graphs, using cell complexes becomes inefficient and impractical. So now we introduce our method, Forge, which is a framework for better representations and better explanations for graphs. So I'll hand over to Sriram for explaining our method and approach.
Hi everyone. So I'm Sriram, and I'm going to be explaining our method, which is Forge. As described by Akshat in the earlier slides, we utilize cell complexes to undo the graph limitations. And so we use cell complexes to model these higher order structures and relations that just graphs alone can't do, and we incorporate them in existing explainers to improve their explainability. How we go about this, we'll explain using Forge. So this is a step-by-step process through which we can explain Forge. First, we have our base graph. Again, the running example will be benzene. This becomes a cell complex through graph lifting. As described by Akshat, we basically add nodes and other augmentations to represent the cell complexes present in the graph. And so we get, this is just a representation. This looks something similar to this. And then the explainer comes in and produces an explanation on this cell complex. Then we get an explanation for a cell complex. An explanation can have some different ways. So what does an explanation usually mean in terms of graphs? It usually gives us a node mask. So if we were to run a graph through an explainer, it usually gives us a node mask and an edge mask, which describes which nodes were important and which nodes were unimportant. And basically, we want this explainer to tell us that these edges are important and any other edge in this graph are unimportant because they do not contribute to the toxicity of the molecule. Only the benzene does, right? So when we pass this cell complex through the explainer, what do we get? We get a cell explanation, which basically means for C0 cells, we have a mask. We can have a mask for C1 cells and C2 cells. Okay, now, how do we go from these cell importances, which is 0, 1, they're the same 0, 1 importances, how do we map it back to the graph importance? This is an algorithm called information propagation. We'll describe this in future slides, but basically it's able to take these cell complexes, cell complex importances, and transfer importance back to the underlying graph where the cells had influence over. And this, in practice, empirically we show that this results in better explanations. And we can see here that the benzene is what's explained. Okay, first things first, lifting the graph. How do we go from this bare bones graph to the cell complex that we care about? It's through graph augmentation, and we have the general algorithm here, but I'll just explain it quickly. Again, the benzene. First, we label all nodes as 0 cells. So in this case, we have 6 0 cells. We're done. For 1 cells, every edge gets its own node. These are 1 cells. And we connect these 1 cells to the nodes which they came from. This is important because this is used later in the info prop algorithm. And finally, cycles, which is this entire face, gets its own node, and we add another augmented node, and this is connected to the 1 cells, edges. Again, in the full complex, we connect them to the 0 cells, but in our reduced complex, we don't. So this is our final complex. And this is extendable to any other structure. As an exercise, you can try doing the same for a pentagon. Okay, information propagation. The bulk of our approach lies in how do we go from cell explanations to graph explanations. And if you think about it, where do we get the cell importance from? In the lifting process, okay, for example, let's take this. If this y is important, what does that tell us? It tells us that the cells that are connected to it are also important. What does that tell us? Well, the edges and nodes that make up those are what's important. And you can think of this in terms of message passing. Basically, these arrow marks are message passing. With message passing, given our cell complex structure, we move importance from 0 cells to 2 cells. So therefore, if a 2 cell is important, it is important because of the edges and nodes that make it up. And this is at the core of our understanding of this algorithm. The details are here. It's a little bit muddy. In fact, we have some other algorithms for when the importance is less than 0.5, in which case we make the importance negative. There's some other tricky things like parameters that we tune during the process. But all you need to understand is, if a cell is important, where do we get the importance from? It's from the underlying nodes and edges that make up that cell. And therefore, we go in the order of reverse message passing through some heuristic. That heuristic is present here. And there are other heuristics that we mentioned in the paper's appendix. We go in the order of reverse message passing to pass the information back to the underlying graph. And these are the steps that make up Forge. Once we have the graph explanation, we can then observe that and see that the hexagon or benzene is what shows up as important. I'm going to be handing it back to Akshit for the results and discussion.
So as Sriram explained, our method is grounded in the understanding that if we have specialized nodes representing cells, these cells actually encode the underlying graph that they're made up of. So the 2 cell here will encode the features as well as the importances of the explainer of this underlying graph. And our approach is to transfer this importance back to these nodes so that the explainer, like the final explanation, is actually in the form of the underlying graph, and all of the if this 2 cell is important, that means that all the underlying vertices are important, etc., etc. So what this gives us is doing lifting. So as Sriram said, we first do lifting, then we train the GNN on complexes, on this complex that we create, on cell complexes. Then we get any underlying explainer. So we have some explainers present here. We get the explanation on the cell complex, right? And then we finally perform info prop, which sort of maps this explanation from the cell complexes back to the underlying graph. That's Forge in a nutshell. So let's look at some results here. So B indicates the base explainer, which is run without any intervention from us. And F indicates the explainer is running with the Forge framework. So as you can see, I'll just underline here. Yeah. So the best result for each data set is in bold, and underline values represent the better result between a base explainer and the Forge variant. So if you see across the table, for almost all data sets and explainers, the Forge variant actually outperform the base variant by quite a lot. So we'll come to this in the discussions as for making some important observations. But you can see that the best performing explainer in each case is a Forge enhanced explainer, except for this one result in MUTAG, in the mutagenicity dataset. However, we show empirically over a large number of datasets that Forge enhanced explainers outperform the datasets in this metric. So I haven't explained the metric yet. The metric is GEA, or graph explanation accuracy, which is basically just the Jaccard score of the nodes that are present in the explanation and are not. So we'll have a ground truth node mask, which will just be zeros and ones, and the vector will be of length n, say if we have n nodes, and then we'll have a pred mask of zeros and ones with the same length n. So all we do is we take pred intersection ground truth over pred union ground truth. In very basic terms, this is GEA. You can look up Jaccard score for more details. However, now we move on to further results, and here we have GEF. So the formula for graph explanation faithfulness is a little more complicated, but what it tells us empirically is that how faithful is the explanation that is generated to the original GNN output. So that basically means, say I have a GNN output on this graph, right? And my explanation actually says that, okay, this edge is not important at all, so you can remove this. So now if I take the GNN output on this graph with the removed edge, how close is the confidence of the GNN with this removed? So ideally what we want is the explanation for a graph should be as close to the model prediction as possible, without like the spurious edges. So what this tells us is, if we remove the right edges or nodes from the graph, the performance of the GNN is not affected. So we ideally want this score to be low. And we show that Forge actually produces explanations that are more faithful to the underlying GNN by quite a factor of around 2 times, I think. So this is another result. And now we come to the observations. So graph explainers can actually be put into different boxes. We have perturbation-based methods, we have gradient-based methods, and we have surrogate-based methods, etc., etc. And so what we find is that perturbation-based methods, which are GNN explainer and subgraph X, so they benefit the most from our framework. So if we go back to the results, for GNN explainer, you can see that the jumps are huge, except MUTAG. But we see that on synthetic, so these are synthetic data sets, and these are real world data sets. So on synthetic data sets, the jump is almost 4 times. And even for subgraph X, we see that the improvements are there for all. And subgraph X actually outperforms every other method in the synthetic dataset testing. So yeah, that's what I said right now. So what another important observation that we make is that some explainers actually perform worse than random. So random is just taking a random explanation, a random node mask, and running it through the metrics. So what we find is that some explainers are actually worse than random. This is very important because being worse than random means that something is seriously wrong in the performance. So what we find is, after applying Forge, all explainers consistently surpass random and achieve significantly improved performance. So our framework actually helps these explainers beat the random baseline. So lastly, our results actually reveal that there is a lot of variability in explainer effectiveness. As you saw, that sometimes GNN explainer was the best, sometimes subgraph X was the best, etc., etc. So what we find is that no single method consistently outperforms across all data sets. So it suggests that the importance of choosing explainers has to be tailored to specific problem domains. So perturbation-based methods might be better for some, gradient-based methods might be better for some other applications. So lastly, we want to talk about the ablations made. So if you remember, Forge is actually made up of two main steps, which is lifting and infoprop. So as an ablation, we wanted to try what will happen if we remove infoprop. So we just do lifting. So here we have the base explainer. Here we have Forge Lift, which just performs lifting. And here we have Forge, which has both lifting and infoprop. So as you can see, so these results are on the synth wheel cube dataset. And we look at 4 explainers. So this is GNN explainer, we have graph mask explainer, and grad explainer, as well as PGM explainer. So various different kinds of explainers. We have surrogate based, perturbation based, gradient based, and another perturbation based method, etc., etc. So across all methods, we find that both lifting and infoprop actually contribute to the increase in performance. So the level of improvement is different. So as we can see in grad explainer, actually lifting does not increase with the accuracy by a lot. However, infoprop does. The reverse is true for PGM explainer, where lifting does all of the heavy lifting and infoprop only adds a slight increase. So what we find is both components are important in making up Forge and giving the accuracy increase that it has. The other ablation that we tried is, if you remember infoprop, the infoprop algorithm had the name hierarchical propagation on it. So we introduced different types of propagations as well in order to see which type of propagation is the best. So we have the ablations here for different data sets. And what we find is that no one method consistently outperforms. So if you see here, so A is hierarchical prop, B is direct prop, C is activation prop, and D is entropy prop. So these are just different variants of propagation that we were testing around with. So for alkane carbonyl, activation prop is the best. For fluoride, hierarchical is the best. Same for hexagon house. But for wheel cube, actually direct propagation is the best. So what this tells us is that the activation, there is no best activation function, there is no best infoprop method to use, and it again depends on the data set and the hyperparameter tuning. So again, the main takeaways from these presentations is that cell complexes are amazing. They are very powerful, and we can use them to model group-wise interaction in graphs. Forge actually exploits these observations, and it results in more human interpretable and more human aligned explanations that are very much improved over the existing ones, over existing explainers. And again, explainers as well as our method Forge, they're often task dependent, and it is important that we choose explainers not arbitrarily, but test them before choosing them. That's all. Thank you.